Next, stability. So we need to talk about stability. It will return to its original position. So there's stable equilibrium. You move this pendulum out of the away, and it'll just return to the beginning. This is where the pin is right at the middle of the disc. You spin the disc, and it'll keep spinning. It won't accelerate. It won't decelerate. So here's the deceleration, if you include friction. Otherwise, it'll just oscillate back and forth forever. Unstable, that's the pencil on its tip. You displace it from equilibrium, it'll just keep going. We want equilibrium that's stable. We want stability. We don't want unstable, unless we're accelerating a rocket or something like that. We want it to keep going. But most of the time, we don't want it to keep going. So let's think about this. We're going to consider problems with 1 degree of freedom. If you have more degrees, then there are methods to handle it, more advanced calculus. Still probably simpler than force equilibrium. That's why we teach this stuff. If the second derivative is greater than 0, it's stable. So there's stability right there. If the second derivative is unstable, like a ball on the top of a bowl, you displace it a little bit, it'll just keep going. Look at these diagrams like you're looking at a cross section of a hill and a ball on the top of the hill. You'll see this in chemistry. You'll see this in almost electromagnetism. You'll see this in almost every field. A potential energy versus coordinate, and Q is a coordinate diagram. You see this all over the place to try to illustrate, well, gee, we found something stable, or gee, this is unstable. Hydrogen fusion is unstable because of this. Now, this is a ball on a flat floor. You displace it from equilibrium, it's neither going to accelerate away, and it's not going to go back to the beginning. All higher derivatives have to be 0 for this. Let me illustrate that. Let me get my pen out. So, for example, a x cubed function is right here. Now, you displace it from equilibrium, this way, it will accelerate back. But then it will just keep going. That's why all higher derivative has to be 0 for neutral equilibrium. Okay, next slide. So let's take a look at this problem here. The spring is unstretched when theta equals 0. Mass is 10 kilograms, so 10 kilograms at the center of mass. That means the potential energy, 1/2 ks squared, so that's the stretching of the spring squared, plus Wy. Now they're following my convention that Wy is the potential energy, gravitational potential energy. The length at theta equals 0, well, the stretching of the spring is going to be 0. So the stretching of the spring, however much, let's get a pen out. So the stretching of the spring is going to be this much. And this is L cosine theta. This distance here is L cosine theta. Let's go back to my laser pointer. So S plus L cosine theta has to equal S. Solving for S. There we go. The height, y equals L over 2 cosine theta. That's going to be important for figuring out the potential energy, gravitational potential energy. So there's that L over 2 cosine theta right there. There's the stretch of the spring. Stretch of the spring, stretch of the spring squared. And now we differentiate that with respect to theta. What's the angle for equilibrium? Okay, dv d theta. From the previous equations, we get this. Sine theta cancels out. By the way, we're setting it equal to 0. So this expression in here is, the rest is math. This theta equals 0 is an unstable equilibrium. Or cosine theta equals this. Or, excuse me, theta equals the inverse cosine of this expression, or 53.8 degrees. Now, let's see if we can talk about stability. Take the second derivative of that potential energy, and you get this expression right here. Put in the two solutions for equilibrium. So at theta equals 0, you get negative, unstable. At theta equals 53.8, you get positive, stable. It's going to drop, which we can see that intuitively, but it's good also to see it with math.